Hi guys, today we are looking at day 6 on long proof completions. So definitely you'll want to make sure that you have your theorem sheet out, theorem definition postulates sheet to reference. So here we go. So if we are given that BC, so this is the line segment BC, is equal to 3 times AB. That's my given, right? So we always write our given as our first statement here. BC equals 3AB, and that's just my given. Next statement that I'm making is that AC is equal to AB plus BC, right? So if we just kind of annotate our diagram here, it's saying that AC, this full length, is equal to AB plus BC. This is just my segment addition postulate. That's literally just a definition of the parts sum to make the whole. So segment addition postulate, we'll just abbreviate. Okay, so knowing that those two parts make the whole, we can next establish that AC equals AB plus 3AB. And this is essentially just like an algebra technique. Notice that I've removed BC from this previous line. Everything else was copied exactly the same. And I exchanged it with 3AB. That was just substitution based on my given. If BC is equal to 3AB, I can just swap the two out. And then finally, just like I'm thinking about algebraic techniques, notice I have essentially a 1AB plus a 3AB. So those can combine to make 4AB. And so we've just found that AC equals 4AB, and that was just by simplification. Okay, next one, we're doing a proof involving a set of angles here. So we are given, remember we always write this first, that the measure of angle ABD is equal to 120 degrees. And we're just writing that as our given statement. Next, we're establishing that angle ABD, which is this guy here, plus angle DBC, which is this angle here, equals 180 degrees. This is just my linear pair theorem. And that theorem just essentially says that if two angles are falling on a straight line, you know, sharing a vertex and a common side, then they're linear angles and they have to add to 180 degrees. And knowing that, I can next go ahead and say that there really should actually be an extra line in here. Now that let's go ahead and maybe just squish it in here, because ideally I would want to say that the measure of angle ABD plus the measure of angle DBC equals 180 degrees. Because when we're summing them, that should actually say measure. Or if you even wanted to just add that in there, I think that's a typo in this proof here. Because we can next say that 120 degrees plus the measure of angle DBC equals 180 degrees. And all we've done here is exchanged or substituted out the measure of angle ABD, that whole expression with 120 degrees. That's literally just utilizing my given information. And we would say, again, that's substitution. It's direct substitution. We're exchanging that expression for its measure. And then once we've done that, we can see that the measure of angle DBC equals 60 degrees. And this is just a matter of subtracting my 180 from, or my 120 from my 180. So I'm actually taking that 120 on the left, subtracting it over to the right, and that's where we end up with 60 degrees. And that is just subtraction property of equality. So we'll just say subtraction prop. So again, just make sure that you're adding that little measure of, because anytime we're actually summing measurements, it should specify that it's the measure. That it's not the angle itself that you can add it. You have to measure add the measures. So just want to make sure you have that added there. Okay, next one, we don't have a diagram, but we are told that angles A and C are complementary, and then angles B and C are complementary. So I can just recap that in my given. Angles A and C are complementary. I would just abbreviate it, our comp. And then angles B and angles C are also complementary. From this, we can deduce that the measure of angle A plus the measure of angle C is 90 degrees, and the measure of angle B plus the measure of angle C is 90 degrees. This is just my definition of complementary angles. Complementary angles. And notice again, like I mentioned, if we're going to actually add angles, we have to add their measures. We can't just add straight away the angles themselves. So that's why we changed from just angle B to measure of angle B. Okay, all right. From there, we can say that the measure of angle A plus the measure of angle C equals the measure of angle B plus the measure of angle C. Because, let's reset our highlighting here. If this full expression equals 90 and this full expression equals 90, they're both the same value, so we can just equate them. And that's just substitution as well. A next thing that we can establish, it's not deducing it from step 3, but it's just kind of a separate consideration, is that the measure of angle C equals the measure of angle C. That's just my reflexive property, right? Remember that a quantity equals itself. And then we're also making this side note that the measure of angle A has to equal the measure of angle B. And this is just my subtraction property of equality, because if we consider that if we already equated these two, measure of angle A, this is in step 3, measure of angle A equals measure of angle C. I'm sorry, measure of angle A plus measure of angle C equals measure of angle B plus measure of angle C. So if I subtract measure of angle C from both sides, then we're left with just A and B equivalent to each other. And then from there, we can take it one step further and say angle A is congruent to angle B. And that's just my definition of congruent angles. If I know their measures are the same, then the angles overall have to be congruent. Okay, lots of words here. Next, we just have a little reminder of how parallel transversal interactions occur. So we say if two parallel lines are cut by a transversal, which is this guy here. Here are my parallel lines in the red. Then the following angles are congruent. We can say that we have, well, there's kind of a coding system here. Notice that these gray angles, those would be corresponding. So we could list that corresponding angles are congruent. In this dynamic, we also know that alternate interior angles are congruent. Alternate interior. We also know that alternate exterior angles are congruent. Right? So the corresponding ones we already labeled, or I did that. You guys spectated. My alternate exterior would be like in purple here with purple here. So they're exterior to the parallel lines and alternate sides of the transversal. And then we could also say that this little guy and this guy here in the green, those are alternate interior. They're both interior to the parallel lines, alternate sides of the transversal. And so we can also say that there are a series of supplementary angles, and those would be, let's kind of reset what we've got going on here. Oh, I should also mention that vertical angles as well are congruent. Lots of congruent angles, right? So vertical would be like this guy and this guy. We have same side interior angles, which are, if I were to label, same side interior, also known as consecutive interior angles. This angle and this angle, right? They're both on the same side of the transversal and they're interior to the parallel lines. Those are classified as same side or consecutive interior angles. Those would be supplementary. And so when we think about adding to 180 versus having the same measure, that's going to kind of change how we can work with things. Okay, number 4, completing the following proof by filling in the blanks. We are given that angle 1 equals angle 3, or is congruent, I should say. Angle 1 is congruent to angle 3. That's my given, okay? So that's already established in line 1 here. Next, we are establishing that angle 1 is congruent to angle 7. So angle 1 congruent to angle 7. That's just definition of vertical angles. So we can say vertical angles definition. Okay. From there, notice that we've just said, okay, angle 1 equals angle 3 is congruent, I should say, and then angle 1 is congruent to angle 7. So that leads us to say that angle 3 is congruent to angle 7. That's by my transitive property of congruence, right? If one quantity is equivalent to a certain value and that same quantity is equivalent to another, then the other kind of accessory values are also going to be equivalent. And then we can take it one step further in step 4 here and say that angle 3 is congruent to angle 5. That is, again, just definition of vertical angles. If I look at my diagram, angle 3 and angle 5 are vertical. So these are my vertical angles. I can say vertical angles definition. And then finally concluding that angle 7 is congruent to angle 5. That is just my transitive property of congruence. Once again, because if we know that angle 5 is congruent to 7, and then angle 3 is congruent to 5, right? So 5 is congruent both to 7 and 3, so that makes, or wait, I was misreading my print there. This was saying angle 3 is congruent to 7. So if 3 is congruent to 7, 3 is congruent to 5, 7 and 5 by association have to be congruent as well, and that's the transitive property. Okay, next one we have a series of parallel lines. They're giving us that information that angle or line A and line B are parallel, and we want to prove that the measure of angle 1 plus the measure of angle 3 is 180 degrees. So first of all, we've thrown down our given. Next, we're establishing that angle 1 is congruent to angle 2. That's just my definition of corresponding angles. We'll say corresponding angles definition, or the fact that corresponding angles are congruent, right? So 1 and 2 are corresponding, so they have to have the same measure. We can take it one step further and say that the measure of angle 1 equals the measure of angle 2. This is my definition of congruent angles. Okay, and again, it's kind of like you have to translate into this nomenclature, like measure of angle 1 instead of angle 1 when you intend to start performing some calculations. So that's why we change it out of the language of just angle 1 to measure of angle 1. Okay, and then next we can establish, well, angle 2 and angle 3 form a linear pair. And that's just the definition of a linear pair, right? 2 and 3 are literally, they have a shared vertex and shared ray, and then they form a straight line. So if we know that they form a linear pair, then we can say that the measure of angle 2 plus the measure of angle 3 equals 180 degrees. And that's just coming from our reasoning that if two angles form a linear pair, they have to sum to 180. And then finally, I can come to my final conclusion, which is the measure of angle 1 equals, or plus the measure of angle 3 equals 180. This is my substitution property, because we already said right up here in line 3 that measure of angle 1 equals the measure of angle 2. So I'm just literally swapping out measure of angle 1 with measure of angle 2. Those two are just being exchanged for one another. And so I'm just like copying down this whole equation, but exchanging those two. Cool. All right, here we go. Last one. We have our given statement that AB, line segment AB, is congruent to line segment CD. That's my given. And I want to prove that AC, which would be this guy, line segment AC is congruent to line segment BD. Okay, so from this diagram and from the information I've been given, I can establish that AB equals CD. This is just my definition of congruent segments. If the line segments are said to be congruent, then their values are actually the same. We're just changing the nomenclature again. Then we know BC equals BC. This is my reflexive property. Literally a thing equals itself. Next, we're going to establish that AB plus BC equals AC. So if I look at my diagram, AB plus BC equals the full AC. That's just my segment addition postulate, just definition of how the parts sum to make the whole. Okay, and then we can next say that CD plus BC equals AC. That is just my substitution property of equality, right? Because we already set up here, AB is equivalent to CD. So wherever I see AB, I can swap it out with a CD, just like it's an algebraic concept. Okay, and so with that being said, we can establish that, well, CD plus BC equals BD. That's again my segment addition postulate, right? Because the parts have to sum to make the whole. And then we can take it one step further and say, well, AC then has to equal BD. And that's my transitive property of equality, because if I rewind, oops, some of my highlighting here, we said that AC up here, AC equals AB plus BC, and BD, wait a minute, what was I going after? BD, oh, no, I'm highlighting the wrong thing. Too many lines here. Okay, so right now we're trying to find, well, the value of AC is CD plus BC. The value of BD is also CD plus BC, right? Those are literally the same. So right here, I'm demonstrating that, well, AC has to equal BD then. That's the transitive property. And then finally, we conclude that line segment AC is congruent to line segment BD. This is, again, definition of congruent segments. So we're just kind of translating it out of the calculation nomenclature to just establishing congruency. Okay, guys, thanks for checking in.